3 billion years. That is how long the rock beneath Central Australia has refused to break. Continents have slammed into it. Oceans have opened and closed around it. The entire history of complex life on Earth has played out on top of it, and it has not moved. Until April 4th, 2026. 36 hours after the strongest geomagnetic storm of the year, something inside that rock finally gave way. And here is what nobody is saying loudly enough. This is now the 5th major earthquake in 14 days, each one arriving in the hours after a solar storm. 4 were on the Ring of Fire, exactly where earthquakes belong. This one was 4,000 kilometers from the nearest plate boundary. Stay with me, because what's driving this pattern is something the textbooks did not prepare any of us for. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss a single update as this story unfolds. Drop a comment with where you're tuning in from, what time it is there, and your opinion on this. Are we seeing a deeper connection between solar activity and Earth's seismic behaviour? Or are we forcing meaning onto a chain of coincidences that only looks connected from the outside? Part 1. The Uluru event that shouldn't exist. Something moved that isn't supposed to move. On April 4th, 2026, at roughly 10 kilometres below the surface of the Australian outback, a magnitude 5.5 earthquake tore through rock that has not meaningfully shifted in over 1 billion years. The epicentre sat 77 kilometres from Uluru, that enormous sandstone monolith rising from the red desert floor, like a fist punching through the skin of the planet. Guests at a hotel near the rock were jolted awake. Light fixtures swung on their mounts, objects rattled off shelves. People stumbled into doorframes, disoriented, reaching for phones, looking for explanations that didn't come quickly enough. There was no structural damage. There rarely is with a 5.5, but the building shook, and that matters, because this building sits on one of the most geologically inert pieces of continental crust that exists anywhere on the surface of the Earth. Let that settle for a second. A magnitude 5.5 on its own is not a catastrophic earthquake. It happens dozens of times a year across the planet. If this had struck southern Japan or central Chile or anywhere along the Ring of Fire, it would have generated a brief news item, a few seismograph printouts, and then been absorbed into the background noise of a planet that never truly stops shaking. Nobody here would be talking about it. But this did not happen in Japan or Chile or anywhere near a plate boundary. This happened in a region of the Australian continent so tectonically inert that the entire country, a landmass roughly the size of the continental United States, averages only about 1 earthquake of magnitude 5 or greater per year. 1 per year. For the whole country. And this was not the only earthquake in the sequence. It was the 5th in 14 days. That is what makes April 4th worth your full attention. To understand why geologists who specialise in crustal mechanics are looking at this event with something between fascination and discomfort, you have to understand what it means for a piece of crust to be described as stable. Not stable in the way a table is stable, where you could reasonably tip it over if you pushed hard enough. Stable in the way that astronomers describe a star as stable, meaning it has existed in roughly the same state for so long that its continued existence seems like a law of nature, rather than a temporary condition. The crust beneath the Australian outback is old. Not old in the way your grandmother's furniture is old, or even old in the way ancient Rome is old. Old in the way that makes human civilization look like a rounding error. The rock beneath this region carries ages measured in billions of years. It has survived the collision of continents. It has survived the opening and closing of oceans. It has watched tectonic plates fracture and reorganize around it, while it remained largely intact, cold, rigid, and unmoved. And on April 4th, 36 hours after the strongest geomagnetic storm of 2026, it moved. Now here is the thread you need to hold in your mind for everything that follows. A sequence of major earthquakes, 5 events across 14 days, appears to be clustering in time immediately after repeated geomagnetic storms. 4 of those events struck along the Ring of Fire, where active fault systems are already under significant stress and tectonic activity is expected. But the 5th event broke that pattern completely. It did not occur at a plate boundary. It did not occur anywhere near a subduction zone or a transform fault, or any of the geological structures we typically associate with earthquake risk. It occurred in the cratonic interior of Australia, roughly 4,000 kilometers from the nearest plate boundary, in a region of ancient rock that conventional seismology would classify as one of the least likely places on Earth for a significant rupture. And it arrived 36 hours after that. G3 geomagnetic storm peaked at a KP index of 6.67. 36 hours, not weeks, not a month, 36 hours. Now, I want to be very direct with you about something before we go any further, because this channel does not do sensationalism dressed up as science. There is no confirmed causal mechanism linking geomagnetic storms to earthquake triggering. What we have is a temporal correlation, a repeated, tightening alignment between solar disturbances and seismic events, and the scientific community is genuinely divided on what that correlation means, or whether it means anything at all. Correlation is not causation. That phrase exists for a reason, and we're going to respect it throughout this entire script. But here is the thing about correlations. When they appear repeatedly, across independent fault systems, across different tectonic environments, and now apparently across the boundary between active fault zones and geologically stable continental interiors, at some point the correlation itself becomes the story, not because it proves a mechanism, but because it demands an explanation. So far, no fully satisfying explanation exists. The earthquake near Uluru is not just a seismic event, it is a classification problem. It does not fit the models we use to describe where and why earthquakes occur. And classification problems in science are not dead ends. They're usually doorways. The question is what's on the other side and whether we're going to have enough seismic data by the end of this sequence to figure it out. Part 2. The Craton Paradox. Geological Impossibility Layer. There is a specific kind of geological structure that scientists call a craton, and if you want to understand why the Uluru earthquake is so deeply strange, you need to understand what a craton actually is, not in the simplified textbook sense, but in the sense of what it means for rock to behave the way cratonic rock behaves. A craton is not simply old rock. It is the cooled, thickened, mechanically rigid core of an ancient continent, a piece of lithosphere that has survived the entire grand cycle of plate tectonics without being subducted back into the mantle, without being significantly deformed by collision, and without accumulating the kind of elastic stress that active tectonic margins build and release through regular seismicity. The Australian continent is home to some of the most ancient cratonic material on the planet. The Musgrave Block, the geological province directly beneath the region where April 4th's earthquake occurred, formed approximately 1.08 to 1.2 billion years ago. The surrounding components of the Australian Shield carry ages approaching 3 to 4 billion years. To put that in a frame that your brain can actually hold, when some of this rock solidified, multicellular life had not yet evolved on Earth. Dinosaurs are a recent development, geologically speaking. The mechanical properties of this kind of rock are what make the April 4th event so difficult to slot into standard seismic models. Cratonic lithosphere is cold in the geological sense, meaning it has been away from the heat of active mantle convection for so long that it has become extraordinarily dense and rigid. It does not bend. It does not accumulate strain the way the thinner, warmer lithosphere near plate boundaries does. Think of the difference between a rubber band and a steel rod. The rubber band stretches and stores elastic energy continuously. Eventually it snaps, and the snap is proportional to how stretched it was. The steel rod resists deformation almost entirely, but if you somehow get it to the point of failure, the failure is abrupt, total, and releases whatever stress had built invisibly within the material. Cratons behave like the steel rod. They are not supposed to snap, but when they do, it is precisely because the stress had no visible surface expression before the moment of rupture. This is what geophysicists call the stress invisibility problem. In active tectonic zones, stress accumulation is relatively measurable. You can watch fault creep, monitor microseismicity, track surface deformation with GPS networks dense enough to detect millimeter-scale movements. The crust is communicating its loading state continuously. In cratonic interiors, that communication is nearly absent. The crust is not creeping. It is not producing a background hum of micro-earthquakes that warns you something is building. It is silent. And silence in a cratonic interior does not mean nothing is happening. It means the measurement tools we rely on in active zones are no longer giving us useful data. That said, let's not pretend this is the first time Australian intraplate crust has failed. The continent has a documented, if rare, history of significant intraplate rupture events. In 1988, the Tennant Creek area in the Northern Territory produced 3 major earthquakes in a single sequence, reaching magnitudes of 6.2, 6.3, and 6.6 respectively, all within 12 hours of each other, all in a region with no prior recorded seismicity of any significance. The ground in the Tennant Creek region literally ruptured the surface, producing a fault scarp that was visible from the air. In 2016, the Musgrave region, the same general geological province as the April 4th event, produced a magnitude 6.1 rupture known as the Petermann earthquake. That event was associated with one of the longest surface ruptures ever recorded for an earthquake of that magnitude, anywhere on the planet. So the region has precedent, but that precedent does not make the timing of April 4th less notable. If anything, the fact that this province has produced significant ruptures before means that it carries some measurable residual stress, and that stress, combined with whatever additional perturbation may have been introduced by the geomagnetic storm, may be precisely what pushed this event over the threshold. And this is where the central question reasserts itself with real force. The Uluru event is not just unusual because it is intraplate, it is unusual because it is the 5th event in a sequence that has been tracking geomagnetic storm timing across entirely different tectonic settings. The first 4 events struck along the Ring of Fire, active subduction zones, and transform boundaries where stress accumulation is ongoing, and where a small additional perturbation might reasonably act as a timing mechanism for a rupture that was going to happen eventually anyway. The argument for those events can be made without invoking anything exotic. But a cratonic interior is different. A cratonic interior is, by definition, a low-stress environment compared to plate margins. The threshold for additional perturbation is theoretically higher, not lower. For the same timing pattern to appear in a region where stress accumulation is supposed to be minimal raises a genuinely unsettling possibility. Either the stress accumulation in the Musgrave block was far larger than current models suggest, or the perturbation introduced by the geomagnetic storm, whatever its physical form, was more significant than anyone has been assuming. Neither of those options is comfortable for the existing framework. Part 3. The solar timing signature. Let's walk through the sequence carefully, because once you lay all 5 events out side by side, something subtle happens in how your brain processes randomness. It stops feeling random at all. Not because it must be connected, but because the timing starts forming a structure that is hard to ignore. We begin on March 24th, when a magnitude 7.5 earthquake ruptures the Tonga-Kermadec region in the southwestern Pacific. This is not an unusual address for seismic energy. It is one of the most violently active subduction corridors on Earth, where the Pacific plate dives beneath the Indo-Australian plate in a steep, almost mechanical descent. These are deep time collision zones, places where the planet is constantly rewriting itself through pressure, deformation, and release. A 7.5 here is serious, but not shocking in isolation. It triggers global monitoring systems, tsunami watch protocols, and a predictable cascade of aftershocks that can last for weeks as stress redistributes along the trench. In other words, a large but expected event occurring in a familiar location and behaving exactly as the models would anticipate. But that is only the first domino. On March 26th, just 2 days later, a magnitude 6.5 earthquake strikes offshore Japan. Japan is not separate from this system, but part of the same vast Pacific stress architecture, sitting on the edge of multiple interacting subduction zones. Still, a 6.5 is a distinct rupture event, not a minor aftershock of Tonga. It is spatially separated, mechanically independent, and occurs too far away for a simple aftershock explanation to hold. Then, just 4 days after that, on March 30th, a magnitude 7.3 earthquake tears through Vanuatu. This becomes the 3rd major rupture in less than a week, all along the Western Pacific Arc, Tonga, Japan's offshore system, and now Vanuatu, each occupying different segments of the Ring of Fire's enormous and interconnected geometry. At this point, we are no longer looking at isolated seismic events. We are looking at something that begins to resemble a regional chain response, or at least a sequence that behaves like one. But the pattern is about to stretch further. On April 1st, a magnitude 7.4 earthquake strikes the Molucca Sea between Sulawesi and Halmahera in Indonesia. Geologically, this is where clarity begins to dissolve. The Molucca Sea region is not a clean subduction interface, but a complex collision zone where arcs actively consume each other, producing a tangled, rotating, three-dimensional stress field. It is one of the most structurally complicated seismic environments on the planet, where stress does not propagate in neat lines, but twists through interacting slabs of crust and mantle. Yet it still joins the same temporal cluster, expanding the sequence to 4 major earthquakes in roughly 8 days across a vast portion of the Western Pacific deformation belt. By now, Tonga Kermadec, offshore Japan, Vanuatu, and the Molucca Sea have all ruptured within a short, compressed window. Each is significant, each is tectonically meaningful, and each sits in a different structural segment of the broader Pacific system. At this stage, a conventional interpretation still holds weight. Clustered seismicity along a globally stressed subduction network is not unusual, and the Ring of Fire is by definition a continuous release system for planetary tectonic energy. But that interpretation is about to be tested by something that does not fit the boundary logic. On April 4th, a magnitude 5.5 earthquake is recorded near Uluru in Central Australia. This is where the sequence stops behaving like a standard tectonic cluster. Uluru sits deep within the Australian craton, one of the oldest and most mechanically stable blocks of continental crust on Earth. This is lithosphere that has survived billions of years of tectonic collisions, rifting attempts, and mantle-driven deformation without breaking in any meaningful plate tectonic sense. Stress does not normally accumulate here the way it does at plate boundaries. Instead, it dissipates across vast, rigid structures that behave more like ancient armour than flexible fault systems. And yet, a measurable seismic event occurs there. It is not catastrophic, but it is geophysically significant precisely because of its location. People in nearby accommodation reportedly felt shaking strong enough to disturb fixtures and dislodge objects, which is not what you expect from one of the quietest tectonic interiors on Earth. This is the pivot point of the entire sequence, because now the pattern has stepped outside the region where conventional stress transfer explanations feel comfortable. Now the second layer enters the picture: space weather. The geomagnetic environment during this 14-day window was far from calm. Earth's magnetosphere was repeatedly disturbed by incoming solar wind streams and coronal mass ejection interactions, keeping the system in a sustained state of electromagnetic agitation. This was not a single isolated solar flare event, but a sequence of disturbances that repeatedly compressed and relaxed the magnetosphere, like a membrane under fluctuating external force. Within this window, each of the major earthquakes occurred within a time frame ranging from a few hours to roughly 2 days after recorded solar disturbances. The Uluru event in particular occurred approximately 36 hours after a G3 geomagnetic storm that peaked at a KP index of 6.67, making it the strongest geomagnetic storm recorded in 2026 at that point. A G3 storm is classified as strong on the NOAA scale. It is capable of affecting satellite orientation systems, disrupting high-frequency radio communication across large portions of the planet, producing auroras visible at mid-latitudes, and inducing electrical currents in long conductive systems such as pipelines and power grids. It is not extreme enough to be catastrophic, but it is far from background noise. Importantly, it also represents a measurable injection of electromagnetic energy into Earth's near-space environment and, through induction processes, potentially into conductive layers of the crust and upper mantle. This is where the discussion becomes more complex because researchers tracking this sequence keep returning to a specific observation. The time lag between solar disturbances and seismic events appears to be shrinking. In the early part of the sequence, delays were closer to multiple days. In the middle, they compressed toward roughly 48 hours. By the time of the Uluru event, the delay appears to have narrowed to about 36 hours. This is sometimes described as latency compression, although whether that reflects a real physical trend or a pattern created by selective perception remains an open question. The challenge is that human cognition is extremely good at constructing patterns from noisy data. If you present enough global seismic events alongside solar activity timelines, the brain will naturally begin drawing connections, even when the underlying process is random. So the real question becomes not whether a pattern can be seen, but whether it persists under statistical scrutiny once bias is removed. To argue that this entire sequence is coincidence requires accepting that 5 significant earthquakes, can occur across multiple tectonic regimes within a 14-day window, that 4 of them align closely with known seismic belts in the Western Pacific, and that one occurs deep within a stable cratonic interior, all while each event falls within hours to a couple of days of recorded solar disturbances. None of these conditions is impossible on its own, but their combined clustering creates a temporal density that naturally invites closer examination. It is important to be precise here. This does not demonstrate that the Sun is causing earthquakes. There is no confirmed causal mechanism that directly links geomagnetic storms to tectonic rupture initiation. However, it does highlight that a growing number of researchers are willing to examine whether indirect coupling mechanisms may exist, particularly through electromagnetic induction processes affecting stress conditions in already loaded fault systems. The most important anomaly in this entire sequence is still Uluru. Boundary faults are easier to explain in clustering models because they are already near failure thresholds and can respond to minor perturbations without requiring any external forcing hypothesis. A cratonic interior event is different. It forces uncomfortable possibilities. Either the interior crust was more stressed than current models assume, or external perturbations are stronger or more distributed than previously understood, or the assumption that cratons are effectively insulated from transient global stress fields needs refinement. What emerges from all of this is not a conclusion, but a tension. On one side, there is a well-understood framework of global seismic variability, where clustering can occur naturally without any external trigger. On the other side, there is a sequence that appears temporally compressed, geographically expansive, and loosely aligned with a period of elevated solar activity that is known to influence Earth's electromagnetic environment. Between those two interpretations sits the real scientific edge of the story, not certainty, but pressure. Pressure to re-examine assumptions about how isolated the solid Earth truly is from space weather influences, and pressure to ask whether what we're seeing is a meaningful coupling between systems that were once considered separate, or simply a coincidence that becomes more persuasive the more closely we look at it. Part 4. Why this event changes the dataset. Scientists and analysts who track global seismicity rely on classification frameworks that exist for one reason above all else: to stop chaos from looking meaningful when it is not. These frameworks are not arbitrary labels or academic tradition. They are built from decades of instrumental records, physical theory, and hard-won observation across millions of earthquakes. At the center of this system sits one of the most important distinctions in all of seismology: interplate versus intraplate earthquakes. Everything in how we interpret global seismic behavior starts from this split, because it defines not just where earthquakes happen, but how they happen, how often they happen, and how predictable their triggering conditions might be. Interplate earthquakes occur at the boundaries between tectonic plates. These are the fault systems everyone is familiar with: the Pacific Ring of Fire, mid-ocean ridges, subduction trenches transform boundaries. They're active, dynamic, and constantly stressed by the slow but relentless motion of Earth's lithospheric plates. Imagine 2 massive conveyor belts grinding past each other or diving beneath one another, never stopping, never relaxing. Stress is continuously injected into these systems, accumulating until it is released in sudden rupture events. In this environment, earthquakes are not rare anomalies. They are expected outcomes of mechanical inevitability. The real question is not whether a rupture will occur, but when it will occur, and how large it will be when it finally releases accumulated strain. Because of this continuous loading, interplate systems have a kind of built-in sensitivity to perturbation. If a fault is already close to failure, even a relatively small external influence can, in principle, advance the timing of rupture. That influence might be stress transferred from a nearby earthquake, subtle changes in pore fluid pressure deep in the crust, tidal forces from celestial bodies, or in more speculative discussions, electromagnetic disturbances associated with space weather. The key idea is not that these systems are easily triggered from nothing, but that they are already primed. They exist near a threshold, and thresholds are inherently sensitive to small nudges. This is why, in a sequence like the first 4 earthquakes in this timeline, the events are not immediately outside the bounds of conventional explanation. Tonga Kermadec, offshore Japan, Vanuatu, and the Molucca Sea all sit within the broad tectonic engine of the Western Pacific. This is one of the most active deformation zones on Earth. where multiple slabs of oceanic crust are being subducted, fractured and reorganized at different angles and depths. Stress interactions across this system are complex and not fully linear. It is entirely plausible, within current models, for stress redistribution following a large rupture in one segment to influence the timing of failure in another segment, hundreds or even thousands of kilometers away, especially when the system is already in a highly energized state. Even if the exact sequence timing is unusual, it is not immediately disallowed by physics. Intraplate cratonic systems, however, occupy a completely different category of behavior. These are the ancient cores of continents, regions like the Australian craton, the Canadian shield, or parts of Central Africa. They are composed of extremely old, thick and mechanically rigid lithosphere that has survived multiple cycles of continental assembly and breakup. Unlike plate boundary zones, these regions do not experience continuous loading from lateral plate motion. They are not visibly accumulating strain in the same way, and they do not produce frequent seismicity that can be used to map stress evolution in real time. Instead, they are often described as stable, though that term is misleading. They are not stress-free, they are simply less obviously active. When intraplate earthquakes do occur, they tend to be sudden, isolated and difficult to forecast. Events like the Tennant Creek sequence or the Petermann Ranges earthquakes in Australia demonstrated that even cratonic interiors can rupture significantly, sometimes producing unexpectedly large events in regions assumed to be mechanically quiet. The stress that drives these intraplate events is not well constrained. It may be inherited from ancient tectonic cycles, locked deep within the lithosphere, or slowly redistributed from far-field plate interactions over geological time. The critical point is that, unlike plate boundaries, these systems do not display a clear, observable progression toward failure. There is no obvious loading curve that tells you when rupture is approaching. This is why the April 4th earthquake near Uluru is so important in the context of this sequence. It forces a direct confrontation with the assumptions built into our classification systems. The Musgrave block and surrounding cratonic structures are not supposed to behave like actively loading fault systems. They are not expected to respond rapidly to external perturbations. In most conventional models, they are the last places on Earth where a small transient forcing, whether from another earthquake or from a space weather event, would be expected to have any measurable effect on rupture timing. Yet here we have a magnitude 5.5 event occurring in this very environment, tightly embedded in a sequence of major earthquakes that unfolded across the Pacific in a compressed temporal window, all of which appear to cluster around periods of elevated geomagnetic activity. This creates a problem of interpretation, not because any single event is impossible, but because the combination begins to stretch across multiple classification boundaries simultaneously. There are, broadly speaking, two ways to interpret what this implies. The first interpretation remains grounded in conservative seismological thinking. In this view, the Uluru region likely contained more residual stress than current global models resolve. Cratonic interiors are not perfectly understood, and stress accumulation in these regions is poorly constrained by direct observation. It is possible that the Musgrave block was closer to a critical failure threshold than expected, and that the geomagnetic storm acted as a minor perturbation, if it had any mechanical influence at all, capable of slightly advancing the timing of a rupture that was already imminent on geological timescales. In this framework, the solar event is not a cause but a potential timing catalyst. The earthquake would have occurred regardless, and the storm merely shifted its timing forward from some unknown future point. This interpretation preserves the integrity of existing models while acknowledging uncertainty in intraplate stress estimates. The second interpretation is more speculative and significantly more challenging to current assumptions. It proposes that the perturbation associated with the geomagnetic storm may have been more than a negligible timing influence, potentially acting through mechanisms that are not yet fully incorporated into standard tectonic models. These mechanisms would have to involve some form of coupling between magnetospheric disturbances and stress conditions within the lithosphere, possibly through induced electric currents, stress modulation along pre-existing microfractures, or fluid migration changes at depth. The physics of such coupling is not entirely prohibited by known laws, but it is not yet established in a way that allows predictive modelling. The distinction between not impossible and not demonstrated becomes critical here, because it defines the boundary between hypothesis and speculation. What makes the Uluru event particularly significant is that it does not sit comfortably in either interpretive category. It is not easily explained as a simple aftershock or stress transfer from the Pacific sequence, given the enormous geographic separation and tectonic independence of Central Australia from the Ring of Fire events. At the same time, it is difficult to treat it as an entirely unrelated coincidence when it occurs within the same narrow temporal window as a series of large earthquakes that themselves appear loosely aligned with periods of elevated solar activity. The result is not a confirmed link, but a clustering of anomalies that begins to accumulate interpretive pressure. If one steps back from the individual events and looks at the sequence as a whole, the most striking feature is not any single earthquake, but the apparent expansion of the affected domain. The first events are firmly within high-activity subduction zones, where large earthquakes are expected and structurally accommodated by plate motion. The later events remain within that same general system, but begin to span broader geographic separation. The final event, however, breaks that boundary entirely by appearing within a cratonic interior that is not typically included in discussions of dynamic plate edge behaviour. Whether this represents a meaningful physical expansion or simply statistical noise is precisely the question that makes this sequence scientifically interesting. If there is any underlying connection, even a weak or indirect one, then what this sequence suggests is not a simple cause and effect relationship between the Sun and earthquakes, but something more subtle, a potential sensitivity of Earth's stress systems to external perturbations under certain conditions, possibly amplified when multiple tectonic regions are already near failure. In that interpretation, the system is not being driven by solar activity, but rather nudged when already primed, with those nudges becoming more visible when viewed across multiple events in a compressed time window. However, it is equally important to recognise that the human brain is exceptionally prone to constructing coherent narratives from temporally clustered events. Given enough global seismicity and enough solar variability, patterns will inevitably appear, even if the underlying processes are independent. This is why seismology and space physics rely heavily on statistical validation rather than visual correlation. Apparent structure is not the same as causal structure, and the history of geoscience is full of examples where compelling patterns eventually dissolved under rigorous analysis. What remains, then, is not a conclusion, but a tension between two interpretations of the same dataset. One interpretation preserves conventional boundaries between space weather and solid Earth processes, treating the sequence as an interesting but ultimately coincidental alignment of independent systems. The other treats the same alignment as a potential hint that these systems may not be as isolated as currently assumed, especially under conditions of elevated global stress. And the uncomfortable part is that both interpretations can still exist within the same dataset without fully resolving each other. The data has not decided the question, it has only sharpened it. Part 5. The Kermadec reactivation problem. The Tonga-Kermadec fault is where this entire sequence begins, and in many ways it is also where the interpretive tension of the whole 14-day window is first established. On March 24th, a magnitude 7.5 rupture propagated through this subduction system in the southwestern Pacific, releasing a significant amount of accumulated strain along one of the most seismically active plate boundaries on Earth. This is not an unusual location for large earthquakes, nor is a rupture of this magnitude unexpected in a statistical sense. The Tonga-Kermadec Trench is part of the broader Pacific subduction architecture, where the Pacific plate is being forced beneath the Indo-Australian plate at a high convergence rate, generating frequent and sometimes very large seismic events over geological timescales. In the immediate aftermath of an earthquake of this size, the surrounding fault system is expected to follow a well-characterized statistical decay pattern described by Omori's law. This relationship, established through decades of empirical observation, states that aftershock frequency decreases over time in an inverse proportion to the time elapsed since the main rupture. In simpler terms, after a large earthquake, the Earth does not immediately return to equilibrium. Instead, it produces a cascade of smaller aftershocks that gradually diminish in both frequency and magnitude. The largest and most numerous of these aftershocks typically occur in the hours and first few days following the main shock, with activity tapering off as the crust adjusts to its new stress configuration. By the time 2 weeks have passed, a system like Tonga Kermadec is generally expected to be in a state of relative settling. It may still produce occasional aftershocks, but these are usually smaller, more scattered, and less structurally significant than the initial sequence. That is not how this system behaved. Instead, what emerges in the data is a secondary phase of activity that begins roughly 13 days after the initial rupture, near the tail end of the same 2-week window that also contains the Molucca Sea event and the intraplate earthquake near Uluru. Rather than continuing a smooth decay into background seismicity, the Tonga Kermadec system begins generating a new cluster of magnitude 5.0 to 5.5 earthquakes, positioned south of the original rupture zone. This spatial distinction is important because it indicates that the activity is not simply a continuation of the original aftershock cloud. It is not concentrated within the immediate rupture footprint where residual stress redistribution would be expected to dominate. Instead, it appears offset along the subduction interface, suggesting a separate segment of the fault system has become newly active. The depth characteristics of these events further sharpen the significance of this observation. These earthquakes occur predominantly within the 10 to 35 km depth range, which corresponds to the shallow to intermediate portion of the subduction interface, where the overriding and subducting plates are mechanically coupled. This is not shallow crustal noise, nor is it deep mantle deformation. It is the interface itself, the primary boundary where stress transfer and rupture propagation occur in subduction systems. The implication is that this is not random adjustment in the surrounding crust, but reactivation along a structurally meaningful segment of the plate boundary. This matters because it introduces a complication into what would otherwise be interpreted as a standard aftershock decay sequence. In a conventional model, the Tonga Kermadec rupture would generate a predictable aftershock sequence that decays over time, with stress gradually redistributing along adjacent segments in a relatively smooth fashion. While it is true that stress migration along subduction zones is a well-established phenomenon where the failure of one segment can increase stress on neighbouring sections and potentially advance their rupture timing, the timing and clustering observed here extend beyond what is typically expected from local redistribution alone. The reactivation of the southern Tonga Kermadec segment occurs within the same compressed temporal window that contains 4 other major earthquakes across the Western Pacific and a significant intraplate event in Central Australia. This overlapping timing raises a more complex question. Are we observing independent stress adjustments across multiple systems that happen to coincide, or is there a broader environmental modulation affecting multiple fault zones simultaneously? What complicates the interpretation further is that the Tonga Kermadec reactivation does not align neatly with a simple aftershock decay model, nor with a straightforward stress transfer chain from the initial magnitude 7.5 rupture. The spatial separation between the original rupture zone and the newly active segment suggests that if stress transfer is responsible, it is operating over a larger and more distributed region than typically modelled. At the same time, the temporal clustering with other global seismic events suggests that this is not an isolated regional phenomenon confined to a single subduction system. When all of these observations are placed onto a single timeline, a more unusual structure emerges. Over approximately 14 days, multiple fault systems across the Western Pacific experience significant seismic activity. These include classic interplate subduction zones such as Tonga Kermadec, offshore Japan, Vanuatu, and the Molucca Sea, all of which are known to produce large earthquakes as part of the normal operation of the Pacific plate boundary system. However, within the same window, the sequence also includes an intraplate earthquake in the Australian craton near Uluru, a location that is not typically associated with active tectonic loading or frequent seismic release. Finally, the original rupture system itself, Tonga Kermadec, appears to generate a secondary phase of activity that does not fit cleanly within the expected aftershock decay pattern. Individually, none of these events require extraordinary explanations. Each can be interpreted within existing frameworks of plate tectonics, stress redistribution, and regional seismic variability. Earthquakes cluster in time even under purely stochastic processes, and the Earth's lithosphere is a complex nonlinear system capable of producing apparent patterns that arise without any external forcing mechanism. However, the difficulty arises not from any single event, but from their collective arrangement in time and space. The temporal clustering across multiple tectonic environments combined with the presence of a cratonic intraplate event and a secondary reactivation of a recently ruptured subduction zone, creates a pattern that is increasingly difficult to dismiss as purely coincidental without careful statistical separation of background variability. This is particularly true when each of these events also appears, at least in timing, to loosely align with periods of elevated geomagnetic activity associated with solar disturbances. It is important to emphasize that none of this establishes causation. There is currently no widely accepted physical model that directly links geomagnetic storms to the initiation of large earthquakes in either interplate or intraplate settings. However, there is ongoing research into possible indirect coupling mechanisms, including the modulation of crustal stress through induced electromagnetic currents, fluid migration changes in fault zones, or small perturbations to already critically stressed systems. These mechanisms remain speculative and are not part of standard operational earthquake forecasting models. What makes this sequence scientifically interesting is not that it proves any of these mechanisms, but that it stretches across multiple domains of expected behavior simultaneously. The Tonga-Kermadec reactivation adds another layer to this complexity, because it suggests that even systems which have already experienced a major rupture are not simply settling in a predictable decay pattern, but may be participating in a broader temporal clustering that extends beyond local stress relaxation dynamics. If one steps back and considers the full 14-day window, what becomes apparent is not a single anomalous earthquake, but a network of temporally linked seismic responses across different tectonic regimes. The Western Pacific subduction zones behave in a way that is broadly consistent with high-energy regional stress redistribution. Yet even within that framework, the timing remains unusually compressed. The Interplate Australian event sits outside this boundary entirely, challenging assumptions about where and how stress perturbations can manifest. And the Tonga-Kermadec reactivation suggests that even previously ruptured systems may not be fully decoupled from whatever larger-scale processes governing the timing of this sequence. The most important aspect of the Uluru event in this broader context is that it continues to function as the extreme boundary case. It is the point in the dataset that pushes furthest away from conventional expectations of tectonic behavior, not because magnitude 5.5 earthquakes are unusual, but because of where it occurred and when it occurred, relative to the rest of the sequence. If the Western Pacific events can be explained within a framework of interacting subduction systems, and the Tonga-Kermadec reactivation can be interpreted as delayed or redistributed stress release, the Uluru earthquake remains the outlier that does not comfortably fit into either category. Taken together, what this 14-day sequence presents is not evidence of a confirmed external driver, but a structured clustering of seismic events that spans multiple tectonic environments and includes both expected and unexpected behaviors within the same temporal envelope. Whether this represents a meaningful physical connection or a statistically interesting coincidence remains unresolved. But what is clear is that the dataset is no longer behaving like a collection of independent, isolated earthquakes. It is behaving like a system under some form of shared timing constraint, even if the source of that constraint has not yet been identified. Part 6. Global Seismic Density Spike. In any given 7-day window, Earth produces a fairly stable number of earthquakes above a chosen magnitude threshold, and this is something seismologists monitor continuously rather than casually observe. The global baseline for magnitude 4.5 and above events typically sits in the range of roughly 100 to 130 earthquakes per week under normal background conditions. This number is not fixed, and it fluctuates in response to natural variability in global tectonic stress release, seasonal modulation in some shallow systems, and random clustering effects that emerge from the nonlinear nature of fault networks. Some weeks fall below that range, some exceed it, and neither deviation is inherently meaningful on its own. The key point in operational seismology is that raw frequency is a blunt instrument. Earthquakes are not evenly distributed events, and counting alone does not tell you much unless you also understand how and where those events are distributed across the planet. What matters far more than total count is spatial and temporal structure. Seismicity is inherently organized along tectonic boundaries, and under normal conditions it presents a recognizable global geometry. The Ring of Fire dominates the dataset with its continuous subduction zones encircling the Pacific Basin, producing frequent moderate and large earthquakes. The mid-Atlantic ridge contributes a steady background of smaller spreading centre events that are usually shallow and well distributed along the ridge axis. The Alpine Himalayan belt adds another broad collision zone where continental convergence produces periodic large ruptures, while scattered oceanic spreading centres and transform faults fill in the rest of the global seismic map. The result is not randomness, but a structured spatial pattern that is stable over time even if individual earthquakes appear unpredictable. In the 7-day window centred on the period we have been discussing, global seismic networks recorded approximately 155 earthquakes of magnitude 4.5 or greater. On a purely numerical level, this is elevated compared to the long-term weekly average. It is not an extreme outlier in statistical terms, but it is high enough to warrant attention, especially when combined with other contextual signals. However, the real anomaly is not found in the number itself. It is found in how those events are distributed across space and time, and more importantly, how tightly clustered they appear to be within a compressed temporal window. During this period, multiple distinct seismic systems showed simultaneous or near-simultaneous increases in activity. The Japan Trench experienced elevated seismicity consistent with offshore subduction adjustment. The Molucca Sea region exhibited swarm-like behaviour consistent with its complex triple-junction tectonics. The Philippine fault system registered a noticeable increase in event frequency, while Papua New Guinea recorded multiple moderate earthquakes across different fault segments. The Kermadec subduction zone not only remained active but appeared to enter a secondary phase of rupture behaviour following its initial major event, and, most notably, Central Australia registered an intraplate earthquake near Uluru, within a cratonic interior that is not typically associated with coordinated global seismic responses. At first glance, it is tempting to interpret this as a simple case of global clustering, which is not unusual in seismology. Earthquakes are known to cluster in time due to stress transfer mechanisms, both static and dynamic, following large ruptures. A significant earthquake can redistribute stress across surrounding fault systems, sometimes triggering subsequent events at considerable distances. This is a well-established phenomenon supported by both observational data and physical modelling. In that sense, a magnitude 7.5 rupture at Tonga Kermadec is entirely capable of influencing stress conditions across large portions of the Western Pacific and potentially even contributing to altered failure probabilities in distant regions through propagating stress waves or long-range static stress changes. However, there is an important constraint embedded in this framework. While stress transfer can explain regional or even sub-regional clustering, it does not easily scale to explain near-simultaneous activation across globally dispersed and geologically disconnected systems. The distances involved in this sequence are not marginal. Japan, Vanuatu, the Molucca Sea, Papua New Guinea and Central Australia are separated by thousands of kilometres and belong to distinct tectonic environments, with no direct mechanical linkage in the traditional sense of fault interaction. The question is not whether one earthquake can influence another nearby system, it is whether a single rupture, or even a cascade of ruptures within the Western Pacific is sufficient to explain synchronous activation patterns that extend beyond the immediate stress field influence zone. This is where the interpretation begins to shift from straightforward tectonic interaction into what some researchers describe as a coordination versus coincidence problem. Earthquake clustering is real, and it is a fundamental feature of nonlinear fault dynamics. However, conventional clustering theory predicts localized cascades, not globally distributed temporal compression. It predicts that events near a main shock are more likely to occur in the aftermath, not that independent seismic systems separated by continental scale distances will all show elevated activity within the same narrow time window. In other words, clustering is expected, but clustering of this spatial scale and simultaneity is not what standard models typically produce. What makes the current dataset particularly intriguing is that the elevated seismicity does not appear to be randomly distributed within the week. Instead, it appears to be organised in time in a way that loosely corresponds with periods of increased geomagnetic activity associated with solar disturbances. This introduces a secondary layer of interpretation that is not part of conventional earthquake forecasting models. The idea that space weather could influence seismic timing is not widely accepted in mainstream geophysics, but it is periodically explored in research contexts that examine indirect coupling mechanisms between the magnetosphere and the lithosphere. If such a coupling exists, it would not operate through direct mechanical forcing in the way that tectonic plates interact with one another. Instead, it would likely involve subtle modulation of stress conditions in already critically loaded fault systems. Proposed mechanisms include the induction of electric currents in conductive regions of the crust, perturbations to pore fluid pressures in fault zones, or very small stress changes acting as timing triggers in systems already near failure thresholds. None of these mechanisms are currently established as predictive tools, and none are considered sufficient on their own to generate large earthquakes. However, they remain areas of ongoing research precisely because the Earth system is complex and not fully understood in its coupled electromagnetic and mechanical behaviour. The critical question raised by this dataset is not whether solar activity directly causes earthquakes, but whether it may influence the timing of rupture in systems that are already primed for failure. This distinction is essential. It separates direct causation from potential modulation, and it changes the scientific framing from deterministic triggering to probabilistic adjustment of failure timing. In that sense, even a weak external influence could, in theory, become visible when viewed across multiple events aggregated over a short time period. However, caution is necessary. Elevated global seismicity within a single week is not, in itself, proof of external forcing. Earth's lithosphere is inherently noisy, and apparent clustering can emerge purely from internal dynamics without any external driver. Statistical fluctuations, aftershock sequences, and stress redistribution across multiple fault systems can all combine to produce periods of apparent global synchrony that are ultimately coincidental. This is why seismologists rely on long-term datasets and rigorous statistical testing rather than short-term visual patterns when evaluating global seismic behaviour. Still, what makes this particular 7-day window notable is not just the elevated count of earthquakes, but the way in which those earthquakes appear to be distributed across multiple independent systems within a tightly compressed temporal frame. The coincidence of elevated activity across Japan, the Western Pacific subduction zones, multiple island arcs, and even an intraplate cratonic region raises questions that are not easily dismissed without careful analysis. The inclusion of the Uluru event in particular complicates the picture, because it extends the apparent response zone far beyond what conventional stress transfer models would typically allow. When combined with the Tonga-Kermadec rupture sequence and the subsequent reactivation of that same system, the dataset begins to resemble something more structured than random variability. It is not yet a coherent mechanism, and it does not yet point to a confirmed external driver. But it does suggest that the temporal organisation of seismicity during this period is unusual enough to justify deeper investigation rather than immediate dismissal. What emerges from this is not a conclusion, but a narrowing of interpretive space. Either the observed clustering represents an extreme but ultimately natural fluctuation within a highly nonlinear global seismic system, or it reflects an incomplete understanding of how multiple Earth subsystems may interact under conditions of elevated stress. In both cases, the data itself remains the same. What changes is the framework used to interpret it. And at the centre of that uncertainty is a simple but important observation. The Earth did not just produce more earthquakes in that week. It produced them in a way that appears temporally compressed, geographically widespread, and loosely synchronized with external solar variability. Whether that structure is meaningful or coincidental is not something the current dataset can definitively resolve. It only makes the question more precise, and in doing so, pushes the boundary of what still needs to be explained. Part 7. The Radiation Belt Anomaly. While all of this was unfolding on Earth's surface, an equally important but less visible process was developing in near-Earth space, and it provides critical context for the broader environmental conditions surrounding this entire sequence of events. The planet's radiation belts, commonly known as the Van Allen belts, are two donut-shaped regions of trapped charged particles held in place by Earth's magnetic field. These belts are not static structures. They breathe, swell, and contract in response to solar forcing, and they serve as one of the most sensitive natural detectors of space weather activity. During the period leading up to the April 4th seismic sequence, these belts were not in a normal equilibrium state. They were in a sustained period of enhancement that lasted for approximately 18 days, which is unusually long by standard geomagnetic timescales. This enhancement was not subtle or marginal, it was measurable and persistent, particularly in the population of high-energy electrons at around 2 MeV, which are often used as diagnostic marker for radiation belt intensity. These electron flux levels were not simply spiking intermittently and returning to baseline, as is typical after a geomagnetic storm. Instead, they were holding within an elevated band, roughly between 3,755 and 6,000 particle flux units, over an extended period. In most documented cases, radiation belt enhancements behave like weather fronts passing through the system. They arrive, intensify for a short period, and then decay as the driving solar wind conditions relax. An 18-day sustained elevation suggests a fundamentally different driving regime, one where energy is being continuously injected or repeatedly replenished faster than it can dissipate. What makes this particularly notable is that there was no single dominant solar eruption during this interval that would normally account for such a prolonged response. There was no isolated, highly energetic coronal mass ejection that could be identified as the primary driver. Instead, the solar environment appears to have been governed by a more complex, overlapping sequence of inputs. One contributing factor was likely a corrotating interaction region, which forms when fast solar wind streams emanating from coronal holes overtake slower solar wind ahead of them. These interaction regions are predictable to some extent because they are tied to the Sun's rotation, and they can produce sustained compression of the solar wind environment near Earth. In addition to this, there also appears to have been residual material from earlier coronal mass ejections still interacting with Earth's magnetosphere during this period. When multiple solar disturbances overlap in time, they can produce a compounded effect sometimes described in space weather research as a stacking of solar wind drivers. In this case, the magnetosphere was not responding to a single clean impulse, but rather to a layered sequence of energy injections arriving from different solar sources. The result is a system that never fully relaxes back to baseline, because each new disturbance arrives before the effects of the previous one have fully decayed. From the perspective of magnetospheric physics, this creates a condition where the radiation belts remain in a kind of sustained excitation state. Energy is being continuously pumped into the system through solar wind magnetosphere coupling processes, including magnetic reconnection at the dayside magnetopores and subsequent energization of trapped particles within the inner magnetosphere. The key point is that this energy does not remain confined to a single region. It circulates, redistributes, and interacts with the ionosphere, creating global-scale electromagnetic perturbations that can vary in intensity over time but remain persistently elevated compared to quiet space conditions. When considering the seismic sequence occurring during the same period, the relevance of this sustained geomagnetic activity becomes a question of coupling pathways. The magnetosphere and ionosphere are electrically active regions, and changes in their state can, in principle, influence the global electric circuit that connects the upper atmosphere to the surface of the Earth. Through this circuit, variations in ionospheric potential can induce small changes in electric fields at the ground level, particularly in regions where crustal conductivity is high or where fault systems are already mechanically stressed. However, the strength and practical significance of this coupling remain subjects of ongoing research, and there is no established consensus that such processes can directly trigger large earthquakes. What is important in this case is not a single spike in activity, but the duration and continuity of the disturbance. An 18-day period of elevated radiation belt flux implies that the near-Earth electromagnetic environment was not experiencing isolated events, but a sustained period of energetic input. This matters because systems that are continuously driven rarely return to equilibrium. Instead, they evolve under persistent stress conditions, and in nonlinear systems like the magnetosphere, small differences in driving conditions can lead to disproportionately large changes in system behavior. Adding another layer of complexity is the timing of the broader sequence relative to known seasonal variations in geomagnetic coupling efficiency. The events in question occurred just after the March equinox period, a time when Earth's orientation relative to the interplanetary magnetic field is particularly favourable for enhanced solar wind magnetosphere interaction. This is described in space physics through the Russell-McFerran effect, which explains why geomagnetic activity tends to peak around the equinoxes. During this alignment, The geometry of the solar wind magnetic field relative to Earth's own field increases the probability of magnetic reconnection, effectively allowing more solar wind energy to enter the magnetospheric system. In practical terms, this means that the same solar wind conditions that might produce moderate effects at other times of the year can become significantly more effective at driving geomagnetic disturbances during equinoctial periods. March and April, therefore, are statistically more likely to experience enhanced geomagnetic activity, not because the Sun is necessarily more active, but because the Earth-Sun geometric relationship is more efficient at coupling energy into the magnetosphere. This seasonal amplification is well documented in space weather research and is one of the reasons why geomagnetic indices often show a semi-annual pattern. The implication of this timing is that the Earth was already in a state of increased susceptibility to solar wind forcing when the radiation belt enhancement began. The system was not operating under neutral baseline conditions. It was operating under a geometry that favours energy transfer within a broader context of sustained solar wind pressure and with a magnetosphere that had not been allowed to fully recover between successive disturbances. This combination creates what space physicists would describe as a persistently driven system rather than a sequence of isolated events. The unresolved question is whether this sustained electromagnetic activity remains confined to the upper layers of Earth's environment or whether it can propagate influence deeper into the coupled Earth system. The transition from magnetosphere to ionosphere is well understood, but the transition from ionosphere to lithosphere is far less clear. Proposed mechanisms for deeper coupling include modulation of telluric currents, small perturbations in crustal stress fields through electromagnetic induction, and indirect triggering effects in fault systems that are already critically stressed. However, none of these mechanisms are currently established as reliable pathways for influencing seismic events at depth. This is why the radiation belt data matters in the context of the seismic sequence, not as evidence of causation, but as evidence of environmental context. It demonstrates that the near-Earth space environment during this period was not in a normal or quiet state. It was persistently energized, dynamically active, and subject to overlapping solar drivers that extended its influence over an unusually long timescale. In systems theory terms, the boundary conditions surrounding the Earth were not stable. Whether that instability can propagate downward into the lithosphere in a way that meaningfully affects earthquake timing remains an open question. But it is precisely the combination of sustained radiation belt enhancement, seasonal geomagnetic amplification, and clustered global seismicity that makes this period stand out for researchers investigating potential cross-system coupling. It does not provide a definitive mechanism, but it does define a highly unusual set of conditions under which multiple Earth systems were simultaneously operating outside their typical baseline states. And in that sense, the significance of the radiation belt anomaly is not that it proves a connection to seismicity, but that it reframes the background. It suggests that the Earth was not simply experiencing isolated geological events during this window, but was embedded within a broader period of extended space weather influence. Whether that influence reaches deep enough to matter for earthquakes is still unknown. But the fact that the system was under sustained electromagnetic stress for nearly 3 weeks makes it a variable that cannot be ignored when evaluating the full context of what unfolded. Part 8. Timing compression effect. What becomes especially important when you step back from individual earthquakes and look at the sequence as a whole is not just where the events occurred, but how tightly their timing appears to line up with shifts in space weather conditions. Instead of treating each earthquake as an isolated point in time, researchers examining this dataset have started organizing them around lag times relative to geomagnetic disturbances. That means asking a very specific question. How long after a measurable change in solar wind or geomagnetic activity did each seismic event occur? When you arrange the 5 key events in this sequence using that framework, a pattern begins to emerge that is subtle, but increasingly difficult to ignore. The Tonga Kermadec earthquake on March 24th appears to have followed a period of elevated geomagnetic conditions associated with a solar windstream arrival roughly 48 hours earlier. The system was already in a disturbed state when the rupture occurred, meaning the lithosphere was not being influenced by a fresh, isolated impulse, but rather by a lingering period of sustained electromagnetic stress in the near-Earth environment. 2 days later, on March 26th, the Japan event occurred within the same broadly elevated geomagnetic background. The lag relationship here is similar in scale, again falling into the multi-day window following the same general solar wind disturbance regime. While Japan and Tonga are part of the broader Pacific seismic system, they are still separated by significant distance and involve different segments of subduction dynamics. The shared timing relative to space weather conditions is what makes the pairing notable, not any direct mechanical connection between the fault systems themselves. On March 30th, the Vanuatu event occurred, again within what can be described as the back half of a continuing geomagnetic disturbance interval. By this point, the system was no longer responding to a single sharp solar event, but to a prolonged period of elevated solar wind driving. The lag time here is shorter in practical interpretation, not because the solar activity was stronger, but because the disturbance state of the magnetosphere had not fully decayed between successive inputs. The Earth system was still effectively inside the tail end of a multi-day energetic environment. The pattern becomes more interesting with the April 1st Molucca Sea earthquake. In this case, the lag between renewed geomagnetic enhancement and seismic response appears to narrow further, falling into the range of roughly 24 to 48 hours after a fresh increase in geomagnetic activity. This suggests that the system was not only remaining in a persistently disturbed state, but that new solar inputs were being layered onto an already elevated baseline, effectively resetting or reinforcing the coupling conditions before each subsequent seismic event. Finally, the April 4th Uluru earthquake introduces the most striking timing relationship of the entire sequence. This intraplate event occurred approximately 36 hours after the peak of a geomagnetic storm that reached a KP index of around 6.67, classified as a G3 level disturbance. Unlike the earlier events, which were embedded within broader multi-day windows of elevated activity, this one sits much closer to a clearly defined peak in geomagnetic intensity. The lag here is shorter, tighter, and more directly aligned with the apex of a measurable space weather event. When these lag times are placed side by side, a structural pattern begins to appear. It is not a clean or mathematically precise trend, but it does show a form of progression. Early in the sequence, the lag between solar activity and seismic response appears to be on the order of days. As the sequence progresses, that lag appears to compress into shorter and shorter windows, eventually reaching a range measured in hours rather than days. If you were to plot these lag intervals on a graph, what you would not see is a flat, random scatter with no relationship between timing and sequence order. Instead, you would see a loosely descending pattern with variability and noise, but an overall suggestion that the response time between geomagnetic disturbance and seismic activity is decreasing as the sequence unfolds. This observed behaviour has been described by some researchers informally as latency compression. It is an attempt to capture the idea that the Earth system, across this period, may have been responding more quickly to external perturbations as the sequence progressed. In other words, the time delay between a solar-driven disturbance and a corresponding seismic event appears to shrink over the course of the 14-day window. If latency compression is a real physical effect rather than a statistical artifact, it forces a very specific kind of interpretation. One possible explanation is rooted in the internal state of the global stress field. Earth's lithosphere is not a uniform structure operating at constant distance from failure. It is a dynamically loaded system, with different fault zones existing at different stages of stress accumulation at any given time. Some faults are relatively stable and far from rupture. Others are already critically stressed and only require a minimal perturbation to slip. Under that framework, the observed compression of lag times could reflect a gradual shift in the global distribution of stress toward criticality across multiple fault systems. As faults approach their failure thresholds, the amount of external influence required to trigger rupture decreases. A system that is far from failure might require a large tectonic or dynamic stress change to initiate an earthquake. A system that is already extremely close to failure might respond to very small perturbations, including potentially subtle external influences that would otherwise be insufficient to trigger activity. In this interpretation, the decreasing lag times would not necessarily mean that the external solar forcing is becoming stronger. Instead, it would mean that the internal Earth system is becoming more sensitive over time. The same level of external disturbance would produce faster and more immediate responses, simply because the system is closer to a tipping point. This would also offer a potential explanation for why an intraplate region like Central Australia could register an event in this sequence. If a normally stable cratonic block was temporarily closer to a critical stress state than expected, then even a weak perturbation might be enough to trigger failure. There is, however, a second interpretation that remains more conservative and methodologically cautious. From a statistical perspective, 5 data points is not sufficient to establish a reliable trend, especially in a system as noisy and complex as global seismicity. Earthquakes are inherently stochastic in their timing, and apparent patterns can emerge simply due to random clustering, especially when the observer is already aware of the external variable being considered. In this view, the apparent compression of lag times may not reflect any physical change in system sensitivity at all. Instead, it may reflect selective perception applied to a small sample size, where a few naturally clustered events create the illusion of a directional trend. This is a critical point because pattern recognition in complex systems is notoriously vulnerable to overfitting. Humans are highly sensitive to sequences and gradients, even when none exist. A small number of events can easily be arranged into a narrative that appears coherent, even if the underlying distribution is entirely random. In that sense, latency compression may be less a physical phenomenon and more a cognitive artifact imposed on an inherently noisy dataset. But even with that caution in mind, the question cannot be dismissed outright, because the implications are significant if the pattern does hold under larger datasets. If Earth's seismic response to external forcing is not constant, but instead varies depending on the evolving stress state of the lithosphere, then earthquake systems cannot be treated as independent local failures driven solely by local conditions. Instead, they would need to be understood as part of a globally coupled system, where external drivers such as geomagnetic disturbances act as weak synchronizing influences across multiple fault networks. That would represent a substantial shift in how seismic risk is conceptualized. Current models largely assume that earthquakes are governed by local stress accumulation and release, with only limited interaction at regional scales through stress transfer mechanisms. A system that exhibits global-scale temporal coupling to external forcing would require a different framework, one that accounts not just for where stress is building, but also for when the entire system may be more receptive to triggering influences. Importantly, even if such coupling exists, it would not necessarily imply predictability in a traditional sense. It would not mean that solar storms cause earthquakes in a deterministic way, nor would it imply that seismic events can be forecast based on space weather alone. What it would suggest is a probabilistic modulation of timing under certain conditions, where the background state of the Earth system determines how sensitive it is to external perturbations at any given moment. At present, the most scientifically responsible conclusion is that both interpretations remain viable within the limits of the data. The apparent latency compression could reflect a real physical process involving increasing system sensitivity, or it could simply be a statistical illusion arising from a small and highly selected dataset. What makes the sequence worth examining further is not that it proves a connection, but that it raises a structured question: whether the timing of seismic events can, under certain conditions, be weakly influenced by external electromagnetic variability. And regardless of which explanation ultimately proves correct, the sequence itself highlights something important. It shows that when earthquakes are viewed not as isolated events, but as part of a temporally ordered system, new questions emerge about how different layers of the Earth-space environment might interact. Whether those interactions are strong enough to matter in a predictive sense is still unknown. But the fact that the timing relationships appear structured enough to even raise the question is what makes this dataset scientifically interesting, and why it continues to draw attention from those studying the boundaries between geophysics and space weather. Part 9. The Kyoto Coupling Model. Physics has to sit at the centre of any serious attempt to connect geomagnetic storms with earthquake timing. Without a physically grounded mechanism, the idea collapses into correlation hunting, where patterns are noticed but not explained. That is not how geophysics advances. If there is a genuine coupling between space weather and seismicity, then there must be a definable pathway for energy transfer, a chain of interactions that begins in near-Earth space, passes through the magnetosphere and ionosphere, and ultimately reaches the solid Earth in a way that can influence fault mechanics. This means moving away from vague assertions and into the specific language of fields, currents, stress perturbations, and material properties. One of the most developed candidate frameworks for such coupling comes from electromagnetic induction theory, applied to the Earth system. This line of research, explored in various forms by groups in Japan, Russia, and the United States, begins with a simple and well-established physical principle. When a magnetic field changes over time near a conductor, it induces an electric field in that conductor. This is Faraday's law of induction, and it is not speculative. It is the same principle that powers electrical generators and explains why long conductive structures on Earth respond strongly to geomagnetic storms. During geomagnetic storms, the Earth's magnetic field is not static. It fluctuates rapidly as solar wind energy is transferred into the magnetosphere through magnetic reconnection processes. These fluctuations can be intense enough to induce measurable electric currents in conductive structures on the surface of the Earth. These are known as geomagnetically induced currents, and they are not theoretical constructs. They have been directly observed and measured during major space weather events. In extreme cases, they have caused operational disruptions in technological systems, most famously in power grids, where long transmission lines act as efficient pathways for induced currents. The key point is that the Earth's crust is also a conductor, albeit a highly heterogeneous one. It is not a uniform block of insulating rock. Instead, it contains a complex mixture of materials with varying electrical properties, including mineral grains, fractured zones, and critically, saline pore fluids that can dramatically increase local conductivity. The conductivity of the crust is not evenly distributed. It is concentrated in specific regions, particularly along fault zones, where fracturing and fluid presence create pathways that allow electrical currents to flow more easily than in the surrounding intact rock. Fault zones, in this sense, can be thought of as natural linear conductors embedded within a much less conductive matrix. They are structurally complex regions filled with broken rock, clay-rich gouge, and often fluid-saturated microfractures. These characteristics make them more electrically conductive than the surrounding lithosphere. This is important because it means that when geomagnetically induced currents propagate through the crust, they are not distributed uniformly. They tend to concentrate along these more conductive structures, meaning that fault zones become natural channels for electromagnetic energy to interact with mechanical systems. This is where electromagnetic physics begins to intersect with fault mechanics. The strength of a fault is not simply a function of the total stress applied to it. Instead, it is governed by a balance between shear stress, which drives sliding, and effective normal stress, which resists it. Effective normal stress is defined as the total compressive stress acting perpendicular to the fault plane minus the pore fluid pressure within the fault zone. This distinction is crucial because it means that changes in fluid pressure can alter the stability of a fault without any change in the external tectonic forces acting on it. If pore fluid pressure increases, the effective normal stress decreases, making it easier for the fault to slip. This is why fluid injection in human-induced seismicity studies can trigger earthquakes. It is not the total stress that changes significantly, but the frictional resistance of the fault itself. This creates a system that is highly sensitive to small perturbations when it is already near a critical state of failure. The proposed link between geomagnetically induced currents and fault activation relies on the idea that these currents can, under certain conditions, produce secondary physical effects within the crust. These effects may include electrokinetic phenomena, where the movement of charged particles within pore fluids generates pressure gradients, as well as localized heating and stress redistribution effects associated with current flow through resistive materials. While each of these effects is typically very small in magnitude, they are not zero. And in a system that is already critically stressed, even very small perturbations can, in principle, influence the timing of failure. This is the key conceptual bridge, the idea that external electromagnetic forcing does not need to create earthquakes directly. Instead, it may only need to slightly perturb the conditions of a fault system that is already close to rupture. In such a scenario, the role of geomagnetic storms would be analogous to a timing signal rather than a primary driving force. They would not generate the energy required for an earthquake, but they might influence the precise moment at which failure occurs. However, when this framework is applied to the full range of events in the sequence under discussion, an important limitation emerges. The electromagnetic induction model is most effective in environments where the crust is sufficiently conductive to allow meaningful current flow. This typically includes tectonically active regions such as subduction zones, volcanic arcs, and young or thermally active fault systems. In these environments, elevated temperatures, high fluid content, and fractured rock structures combine to create efficient pathways for induced currents. The challenge arises when considering stable continental interiors, such as cratonic regions. These areas are characterized by cold, ancient, and relatively dry lithosphere. The rocks are typically more intact, less fractured, and contain fewer conductive fluids. As a result, their bulk electrical conductivity is significantly lower than that of tectonically active zones. This means that the efficiency of electromagnetic induction in these regions is greatly reduced. Induced currents are weaker, more diffuse, and less likely to concentrate in a way that would meaningfully perturb fault stability. This is where the April 4th event near Uluru becomes particularly difficult to explain within a purely induction-based framework. The Musgrave Block, part of the Australian cratonic interior, is not typically considered a high conductivity environment. Standard models of geomagnetically induced current propagation would predict relatively weak coupling between space weather disturbances and crustal stress conditions in such a setting. Yet the timing of the event appears to align with a period of elevated geomagnetic activity, similar to the timing relationships observed in more tectonically active regions earlier in the sequence. This mismatch does not invalidate the induction model, but it does expose its incompleteness. If the mechanism works well in conductive fault zones, but appears to extend into low conductivity cratonic interiors, then either the properties of those interiors are not fully understood, or additional processes are contributing to the observed timing relationships. One possibility is that localized structural features within the craton, such as buried fault zones, ancient suture boundaries, or fluid-rich deep crustal pockets, may create localized conductivity anomalies that are not captured in broad-scale geological models. Another possibility is that the magnitude or structure of the geomagnetic disturbance during the peak event was sufficient to produce deeper or more widespread induction effects than typically assumed. Extreme geomagnetic storms are known to expand the spatial reach of induced currents, and their effects can propagate into regions that are normally considered weakly coupled to space weather activity. In such cases, the standard assumptions about conductivity thresholds may not fully apply. What this means is that the induction model, while physically grounded and well supported in principle, does not yet fully resolve the observed pattern across all 5 events. It provides a plausible explanation for why tectonically active regions along the Ring of Fire might show timing correlations with geomagnetic disturbances. It establishes a mechanism that links space weather to fault zone physics in a way that is consistent with known electromagnetic and mechanical processes. But it does not fully account for why a stable continental interior would appear to respond on a similar timescale. That gap is not a failure of the model, but a signal of where the current understanding is incomplete. It suggests that either the electrical structure of cratonic lithosphere is more complex than currently mapped, or that additional coupling pathways exist that are not yet fully integrated into mainstream geophysical models. These could include deeper mantle lithosphere interactions, unrecognized conductive structures, or nonlinear threshold effects in fault systems that are more sensitive to weak external forcing than traditionally assumed. This is where the physics discussion reconnects directly with the broader pattern. The induction framework provides a credible, experimentally grounded pathway for electromagnetic influence on fault mechanics, but it does not fully close the loop across all observed cases. The Ring of Fire events fit comfortably within its explanatory range, the cratonic event does not. And that mismatch becomes the most important scientific feature of the entire sequence. Rather than weakening the hypothesis, this tension defines its boundary conditions. It shows where current models succeed, where they strain, and where new data is needed. The question is no longer whether electromagnetic induction can influence faults in principle. It can. The question is how far that influence extends across different geological environments, and whether the combination of space weather intensity, subsurface conductivity variations, and pre-existing stress conditions can extend that influence farther than standard models currently predict. In that sense, the Uluru event is not an anomaly to be dismissed. It is a test case. It forces the question of whether the Earth system, as currently modelled, fully captures the depth and variability of its own electrical structure. And until that question is resolved with more data and more detailed subsurface mapping, the induction model remains both a powerful partial explanation and an incomplete one. Part 10. The Craton Problem. Return to the Musgrave block because this is where the entire interpretation either holds together or starts to unravel. The difficulty here is not solved by invoking electromagnetic induction alone, not resolved by pointing to the fact that intraplate earthquakes do occasionally occur in Australia, and not answered by simply stating that a magnitude 5.5 event requires a significant pre-existing stress field. Each of those statements is partially true, but none of them address the deeper structural problem exposed by the April 4th rupture. The Craton issue is not a single unknown. It is a stack of interacting uncertainties that amplify each other in a way that makes the system fundamentally harder to characterize than tectonically active regions. The first uncertainty sits at the most basic level, the actual stress state of the deep cratonic crust. Unlike plate boundary zones, where dense networks of seismic instruments, GPS arrays, and repeated rupture histories allow relatively tight constraints on stress accumulation and release cycles, the interior of the Australian craton is sparsely instrumented. In the Musgrave Block region specifically, the observational density drops significantly compared to active margins. There are seismic stations, but they are widely spaced. There are geodetic measurements, but they primarily capture surface deformation rather than deep stress distribution. There are geological inferences from past rupture events, but those are episodic snapshots rather than continuous measurements of loading. This creates a fundamental blind spot. Surface GPS networks can detect millimeter-scale deformation across broad regions, and they are extremely useful for understanding plate motion and long-wavelength strain accumulation. However, they are not sensitive enough to resolve stress concentrations at depth on individual fault structures that may be critically loaded. Deep borehole stress measurements, which would provide direct insight into in-situ stress conditions, are extremely limited in this part of Australia. As a result, we are left with an incomplete picture. We know that the Musgrave Block is capable of producing significant earthquakes because it has done so historically, including events in the magnitude 6 range. What we do not know is how close individual faults are to failure at any given moment. The system is not necessarily quiet, it is under-observed. This leads to a subtle but important inversion in how stability is often assumed in cratonic regions. Stability is frequently interpreted as a lack of activity, but in reality it may simply reflect a lack of detectable release events. If a fault system accumulates strain slowly over very long timescales and releases it only occasionally in moderate to large earthquakes, then long periods of apparent inactivity do not necessarily indicate low stress. They may indicate stress that is being stored and redistributed in ways that are not visible with current instrumentation. The second uncertainty concerns the electrical structure of the cratonic lithosphere, which is central to evaluating any electromagnetic coupling mechanism. The induction-based framework depends critically on the presence of conductive pathways through which geomagnetically induced currents can propagate. At the surface, the Australian craton is dominated by Archean and Proterozoic rocks that are generally cold, dry, and electrically resistive. On that basis alone, one might conclude that electromagnetic coupling effects should be weak in this environment. However, the deeper structure of the crust complicates that assumption. Geophysical studies using deep seismic reflection profiling and magnetotelluric surveys have revealed that the continental crust is not uniformly resistive with depth. Instead, it is often layered, with zones of significantly higher conductivity appearing in the lower crust in many cratonic regions. These conductive layers are not fully understood, but they are commonly associated with the presence of fluids, partial melts, or specific mineral assemblages such as graphite-bearing shear zones that can dramatically increase electrical conductivity even in otherwise stable continental interiors. In Australia specifically, there are indications from geophysical surveys that some parts of the craton contain deep conductive anomalies. Whether these anomalies are continuous, how they are distributed beneath the Musgrave Block, and whether they intersect with the fault structures that ruptured on April 4th are all open questions. There is no high-resolution, three-dimensional conductivity map of the crust beneath that region at a scale sufficient to definitively rule in or rule out efficient induction pathways. That absence of resolution matters, because it means that the assumption of electromagnetic decoupling in cratonic environments may be based more on surface geology than on deep structure. If conductive pathways exist at depth, even intermittently or in localized zones, then the potential for geomagnetically induced currents to penetrate deeper into the crust than expected becomes non-trivial. It would not require the entire craton to be conductive. It would only require connectivity between the induced current systems and specific fault zones that are already mechanically sensitive. In that case, the induction model does not fail in cratonic settings, but instead becomes highly dependent on poorly constrained subsurface heterogeneity. The third uncertainty is more conceptual and in some ways more fundamental than the first two. It concerns the definition of stability itself in a continental interior that has been subject to far-field tectonic forces for over 1 billion years. The Australian craton is often described as stable because it is located away from active plate boundaries. But this description can be misleading if it is interpreted to mean mechanically isolated or stress-free. In reality, the Australian plate is not stationary or isolated. It is moving northward at one of the fastest rates of any continental plate, colliding with the Eurasian and Pacific plates at its margins and transmitting stress fields across its interior. These far-field tectonic stresses do not terminate at the plate boundaries. They propagate through the lithosphere as broad, low-amplitude deformation fields. Over geological timescales, even small stress contributions can accumulate. In a rigid, long-lived craton, where deformation is not easily accommodated by continuous ductile flow or frequent small earthquakes, stress can build in complex non-uniform ways. Some regions may remain relatively unstressed, while others may accumulate localized stress concentrations along ancient structural weaknesses, inherited shear zones, or reactivated fault systems. The Musgrave Block sits within this context. It is not an isolated mechanical island. It is part of a continental interior that is slowly, continuously, and unevenly responding to boundary forces acting thousands of kilometers away. Over hundreds of millions to billions of years, these small but persistent stress contributions can accumulate in ways that are difficult to reconstruct from present-day observations. The critical point is that we do not have a reliable high-resolution model of the absolute stress state in the deep crust of this region. We have models of relative motion and surface strain, but not of absolute stress accumulation at depth. This leads to a convergence of uncertainty. The stress state is poorly constrained, the conductivity structure is incompletely mapped, and the definition of stability itself becomes ambiguous when viewed over geological timescales. Together, these three factors mean that the Musgrave Block cannot be treated as a simple end member of stable crust, in which external perturbations are assumed to have negligible effect. It is instead a complex, under-observed system with unknown proximity to failure in specific fault zones. When these uncertainties are combined, the interpretation of the April 4th event becomes significantly more complicated. The rupture cannot be easily classified as either fully expected or fully anomalous. It sits in a region of parameter space where both stress conditions and coupling pathways are insufficiently known to make a definitive prediction about sensitivity to external forcing. This is precisely why the event is scientifically interesting. It exposes the limits of current observational coverage and modelling capability. Within this framework, the induction model does not fail, but it becomes conditional. It may explain timing influences in well-conductive, well-instrumented tectonic environments with relatively high confidence. It may become weaker or more uncertain in cratonic interiors unless specific subsurface conditions are met. But whether those conditions exist beneath the Musgrave Block is not currently known. That unknown is not a minor detail, it is the central missing variable. What emerges from this is not a conclusion about causation, but a clearer definition of ignorance. The Musgrave Block event forces three independent unknowns into the same analytical space at once: the true stress state at depth, the true electrical connectivity of the crust, and the true mechanical interpretation of long-term stability in a slowly deforming plate interior. Each of these uncertainties alone would be manageable. Together they define a system that cannot yet be fully constrained. And that is why the April 4th rupture matters beyond its magnitude or location. It does not prove a solar seismic connection. It does something more important from a scientific perspective. It highlights exactly where the current models stop being able to distinguish between low probability coincidence and incomplete physics. In geophysics, that boundary is not a failure point. It is where new measurement, better instrumentation, and deeper modelling begin to matter most. Part 11. Multizone synchronization. Question. Now pull back and look at the full picture as it stands, because when you place all the events on a single timeline, the pattern is not subtle. It reads like a chain reaction unfolding across the planet's most active seismic corridors, with one unexpected outlier sitting deep inside a continental interior. First, the Tonga-Kermadec system opens the sequence on March 24th with a major rupture, and then does something even more interesting. It does not simply return to baseline. Instead, it begins showing renewed swarm-like activity south of the original rupture zone, as if the system is still redistributing stress after the initial failure. Then, just 2 days later, the Japan Trench responds on March 26th with its own significant seismic adjustment. By March 30th, Vanuatu enters the sequence. On April 1st, the Molucca Sea follows. And finally, on April 4th, you have the Musgrave Block event in Central Australia, a magnitude 5.5 earthquake in a region that is not supposed to behave like that on human timescales. Surrounding all of this is a broader geophysical backdrop that cannot be ignored if you are trying to interpret timing rather than just magnitude. There is an 18-day window of elevated radiation belt activity, indicating sustained disturbance in near-Earth space environments. There is a strong G3 class geomagnetic storm occurring near the end of that window, marking a period where the Earth's magnetosphere is being repeatedly compressed, stirred, and reconfigured by solar wind pressure and magnetic field variability. And most importantly, there is a spatial distribution of seismic events that stretches across nearly the entire Western Pacific subduction system, while also reaching into the Australian craton, a region that is typically considered tectonically stable on short timescales. When you lay these components side by side, the uncomfortable observation is not that any single earthquake is unusual. It is that so many distinct systems appear to be locally active within the same, relatively narrow temporal window. The central question, the one that this entire sequence forces into view, is why this window exists at all. Why does the Ring of Fire, the Kermadec system, the Japan Trench, the Vanuatu Arc, the Molucca Sea region, and even the Australian interior all register notable seismic activity within roughly the same 14-day period? There are two broad frameworks for thinking about this, and they currently sit side by side without resolving into a single accepted explanation. The first is a framework of causal coupling, and the second is a framework of temporal coincidence shaped by internal Earth dynamics and statistical clustering. In the causal coupling framework, something external to the solid Earth system is acting as a synchronizing influence. That something does not need to be imagined as a direct trigger that creates earthquakes from nothing. Instead, it would function more like a timing perturbation, a small but globally distributed influence that interacts with faults already near critical stress thresholds. In this view, geomagnetic activity, ionospheric disturbances, and electromagnetically induced currents in the crust are not primary drivers of seismicity, but modulators of rupture timing. They would not determine where earthquakes happen, but they might influence when a fault that is already critically stressed finally crosses the threshold into failure. This is an important distinction because it moves the hypothesis away from simplistic cause and effect thinking and toward a more nuanced view of nonlinear systems, where small perturbations can shift the timing of large releases of stored energy. In the alternative framework, none of this external coupling is necessary. Instead, what you're seeing is a combination of normal tectonic processes, stress transfer, and statistical clustering. Large earthquakes are not isolated events in a strict sense. They are part of a dynamic system where stress is constantly redistributed. The Tonga-Kermadec rupture could have altered stress fields across parts of the Western Pacific, potentially increasing failure probability in nearby subduction zones through dynamic triggering or static stress changes. That would make subsequent activity in Japan, Vanuatu, and the Molucca Sea more likely within a short time window. From this perspective, the apparent synchronization is an illusion created by the natural tendency of large earthquakes to cluster in time following a major event in a highly stressed region. The solar and geomagnetic activity occurring during the same period would then be unrelated background variability, coincident in timing but not causally connected. The difficulty is that neither framework fully closes the explanatory loop when you include all the observations at once. The tectonic coupling model struggles to naturally incorporate the Musgrave block event. Dynamic stress transfer from a subduction zone rupture in the southwest Pacific does not easily propagate into the deep interior of the Australian craton with sufficient strength or coherence to influence a magnitude 5.5 earthquake thousands of kilometres away. Static stress changes decay too rapidly with distance, and dynamic waves, while capable of triggering distant seismicity in some contexts, typically interact more strongly with already critically stressed fault systems in tectonically active regions rather than stable continental interiors. This does not make a connection impossible, but it pushes it toward the edge of plausibility under standard assumptions. On the other hand, the causal coupling framework faces its own structural challenge, which is that it requires a physically consistent pathway linking solar variability to crustal stress modulation at a level capable of influencing fault timing. This is where mechanisms such as geomagnetically induced currents become relevant. During periods of geomagnetic disturbance, time-varying magnetic fields interact with the Earth's conductive layers, inducing currents that flow through subsurface structures. These currents are not hypothetical. They are directly measured in power grids during geomagnetic storms and are known to produce operational disruptions. The extension of this phenomenon into the solid Earth system suggests that similar currents can flow through conductive regions of the crust, particularly where fluids, fractured rock, and mineralized fault zones provide pathways for electrical conduction. The key unresolved question is scale. In active tectonic margins, where the crust is warmer, more fractured, and more fluid-rich, these induced currents have a more plausible route to interacting with fault mechanics through electrokinetic effects, fluid pressure perturbations, or localized heating. In stable cratonic interiors like the Musgrave block, however, the crust is typically colder, drier, and more resistive. That makes the induction pathway weaker, less continuous, and less efficient at transmitting electromagnetic energy into mechanical stress changes. This is why the Musgrave event becomes such an important outlier in the dataset. It forces you to confront whether our assumptions about electrical conductivity and mechanical stability in cratonic lithosphere are complete enough to rule out subtle coupling mechanisms, or whether there are deeper conductive structures and stress concentrations that remain unmapped. What emerges from all of this is not a clean answer, but a structured uncertainty problem. The Western Pacific events sit comfortably within known patterns of subduction zone clustering, where stress transfer and dynamic triggering are well-established phenomena. The solar and geomagnetic activity provides a temporally aligned external forcing environment that is known to interact with the Earth system in measurable ways, even if the seismic connection remains statistically debated. And the Musgrave block event sits at the intersection of these two domains, where neither internal clustering mechanisms nor external coupling models can fully account for its timing without introducing additional assumptions about deep crustal structure and stress state that are not currently constrained by direct observation. The broader implication is that the Earth system may not be strictly separable into independent fault systems evolving in isolation. Instead, it may be a hierarchy of interacting subsystems, where tectonic stress evolution dominates long-term behavior, but shorter-term timing modulation can, under certain conditions, be influenced by external electromagnetic forcing. If that is even partially true, then the way we currently model seismic hazard, particularly in regions assumed to be stable, may be missing a layer of temporal variability that does not change where earthquakes occur, but could subtly influence when they occur within already loaded systems. The significance of that distinction becomes clear when you consider infrastructure planning, risk windows, and the assumption of temporal randomness that underlies many probabilistic seismic hazard models. At the present stage, the honest position is that the dataset is too small and too mixed to collapse into a single definitive interpretation, but it is large enough and structured enough to resist dismissal as pure coincidence. It sits in a space where known tectonic physics explains parts of the sequence well, space weather physics explains parts of the environmental context well, and neither framework alone fully accounts for the apparent synchronization across such diverse geological settings. That is exactly the kind of boundary condition where scientific understanding tends to evolve, not through immediate resolution, but through the gradual accumulation of events that either strengthen one framework or forced the development of a more unified model that can accommodate both internal Earth dynamics and external solar forcing within a single coherent system. Part 12. The Expanding Footprint Hypothesis. Here is what this sequence is not. It is not evidence that the Sun is directly controlling earthquakes in a deterministic or predictable way. It is not a signal that the planet is approaching a synchronized, globally triggered seismic catastrophe initiated by solar activity. It is not validation of historical forecasting schemes that attempted to use solar cycles or geomagnetic indices as standalone earthquake prediction tools. Those approaches have been tested repeatedly, and under rigorous statistical scrutiny, they have not produced reliable predictive power at the level required for operational forecasting. The scientific consensus does not support a simple solar-to-earthquake causal pipeline, and treating the present sequence as proof of such a mechanism would be a misreading of both the data and the limitations of the current observational record. What the sequence does appear to represent is something more subtle, and in some ways more interesting precisely because it is more constrained. It aligns with a line of inquiry that has existed at the edges of geophysics for decades, the hypothesis that geomagnetic disturbances do not generate earthquakes, but may influence their timing in systems that are already close to failure. In this framework, the Earth's tectonic system remains the primary source of energy accumulation and release. Stress builds over long timescales through plate motion, mantle dynamics, and crustal deformation. Earthquakes occur when that stress exceeds the mechanical strength of faults. Nothing external replaces that mechanism. Instead, external forcing, if it plays a role at all, acts like a small perturbation on an already loaded system, potentially shifting the exact moment of rupture. This is the critical distinction that prevents the idea from collapsing into pseudoscience. It is not a claim of causation in the strong sense. It is a claim about timing sensitivity in nonlinear systems. In physical terms, many complex systems exhibit threshold behavior. They remain stable under increasing load until a tipping point is reached, after which a relatively small perturbation can determine the precise moment of transition. In that narrow window, even weak external influences can become relevant not because they supply energy comparable to the main driving force, but because they interact with a system that is already dynamically unstable. In the case of geomagnetic disturbances, the proposed mechanism is not speculative in the sense of being invented without foundation. It is grounded in known electromagnetic processes. When the Earth's magnetic field fluctuates rapidly during geomagnetic storms, it induces electric currents in conductive materials at and below the surface. These geomagnetically induced currents are well documented in engineering systems, particularly in long-distance power transmission networks. They are strong enough to disrupt transformers, distort grid behavior, and require active mitigation strategies during severe space weather events. The Earth's crust is also a conductor, albeit an uneven and highly heterogeneous one, composed of mineral structures, fractured rock, and fluid-filled pore spaces. Fault zones in particular often exhibit enhanced conductivity relative to surrounding rock due to elevated fluid content and deformation-induced permeability. Within this framework, the hypothesis is that induced currents could, under certain conditions, interact with fault zones in ways that slightly modify stress conditions. The proposed pathways include electrokinetic effects, where fluid movement is influenced by electrical fields, thermal effects, where localized heating alters material properties, and pore pressure modulation, where small changes in fluid pressure alter the effective normal stress on a fault. These effects are not large. In most contexts, they are negligible compared to tectonic forces. But in a fault system already near critical stress, even a very small perturbation could, in principle, influence the timing of rupture. The implication of this hypothesis is not that solar storms create earthquakes, but that they might act as a timing modulation factor within a narrow subset of already critical systems. If correct, this shifts the interpretation from cause to clock adjustment. Earthquakes remain internally driven, but their occurrence time could be slightly advanced or delayed within a short window, relative to their natural failure point. This distinction matters because it reframes how such a hypothesis would be evaluated. The relevant question is not whether solar activity correlates with global earthquake occurrence in a broad statistical sense. It is whether, during periods of elevated geomagnetic disturbance, there is a measurable shift in short-term seismic probability in specific fault systems that are already in a high-stress state. That is a far more constrained and testable claim than global prediction. It is also far more difficult to evaluate because it requires high-resolution temporal data, accurate stress state estimation, and careful separation of coincidental clustering from true modulation effects. When this logic is extended to the Musgrave block event, the implications become more complicated. Cratonic interiors are not typically considered sensitive environments for external modulation because they are generally cold, mechanically strong, and electrically resistive compared to tectonically active margins. This makes them poor candidates for strong electromagnetic coupling under standard assumptions. However, the presence of a magnitude 5.5 earthquake in such a region during a period of elevated geomagnetic activity forces a more careful examination of those assumptions. It does not prove a causal link, but it does expand the boundary conditions of what must be explained. Now extend that logic outward to the full sequence, and the scale of the interpretive challenge becomes clearer. The pattern includes major subduction systems in the Western Pacific, including Tonga Kermadec, Japan, Vanuatu, and the Molucca Sea, all of which lie within the most seismically active region on Earth. These systems are known to produce earthquake clustering through well-understood mechanisms such as stress transfer, slab interactions, and dynamic triggering from seismic wave propagation. Within that region, temporal clustering over periods of days to weeks is not unusual following a large rupture. The Tonga Kermadec event provides a plausible internal driver for at least part of the subsequent activity. However, the addition of a cratonic interior event during the same temporal window introduces a structural asymmetry into the dataset. It expands the spatial footprint beyond the region where internal tectonic coupling is most efficient. It forces consideration of whether a secondary modulating influence might be operating across both high activity and low activity tectonic regimes simultaneously. This is where the space weather context becomes relevant, not as a deterministic driver, but as a potential common temporal background influencing systems with different internal dynamics. The sequence also occurred during a period of sustained geomagnetic and radiation belt activity spanning approximately 18 days, culminating in a G3 class geomagnetic storm. This timing overlaps with the equinox period, when geomagnetic coupling efficiency is known to be enhanced due to the orientation of Earth's magnetic field relative to the solar wind. These are not rare conditions in a strict sense, but they represent a statistically elevated environment for electromagnetic interaction between solar and terrestrial systems. Solar cycle 25 has also been more active than some pre-cycle predictions anticipated, increasing the frequency of such periods relative to quieter solar minima. What this means in practical terms is that the conditions present during the seismic sequence are not exotic outliers. They are representative of an active phase of the current solar cycle. If any coupling mechanism between geomagnetic activity and seismic timing exists, even a weak one, it would be expected to manifest most clearly during exactly these kinds of intervals. That does not confirm the mechanism. It simply identifies where such a mechanism would be most likely to become detectable if it exists at all. From a hazard perspective, the most important implication is not prediction, but classification. Traditional seismic hazard models divide the Earth into regions of varying baseline risk, based on tectonic setting, historical seismicity, and known fault structures. Cratonic interiors are classified as low-risk environments because their recurrence intervals for significant earthquakes are extremely long relative to human observation periods. This classification is statistically valid under purely internal tectonic models. However, if there exists any external modulation of rupture timing, even at a very small amplitude, then the assumption of strict temporal independence between fault systems may need refinement. That does not imply a rewriting of seismic hazard maps. It implies a more nuanced understanding of temporal variability within those maps. In other words, the spatial footprint of risk may remain largely unchanged, but the temporal distribution of that risk could, under certain space weather conditions, become slightly more concentrated than baseline models assume. Ultimately, what the sequence from Tonga Kermadec to Uluru demonstrates is not a conclusion, but a boundary condition. It sits at the intersection of well-established tectonic physics, well-documented geomagnetic processes, and an unresolved question about whether those two domains interact in measurable ways at the level of seismic timing. The evidence is not sufficient to confirm coupling. but it is structured in a way that makes the question harder to dismiss outright than it would have been before this sequence occurred, and that is where the scientific significance actually lies. Not in certainty, but in constraint expansion. Not in proving a mechanism, but in identifying where existing models are least complete. The system has not revealed a new law of nature. It has revealed a gap in the boundary between two well-modelled systems, the dynamic Earth beneath our feet and the variable space environment surrounding it. Whether that gap turns out to be physically meaningful or statistically illusory is still unknown, but it is now clearly defined enough that it can no longer be ignored.